Last week, we looked at a typical hood system, a typical exhaust ventilation system. Idea is we want to protect the worker from some exposure that he's going to that he has based on what kind of work he's doing, grinding, working with solder, working over a heated bath, cleaning, solvent cleaning materials. So the first thing we need is a device to capture and pull the contaminant and also the air around that area away from him and into a device that's going to capture it and take it away. So that's going to be a hood. Anything that does that is going to be basically hood. A hood can consist of just a plain opening in the end of a round duct. It could be a piece of flex duct. It could consist of a bell-shaped device on the end of a piece of flex duct or straight duct. It could be elaborate, like a thing that's very elaborate, like slots at the back of a bath of solvent for dipping in parts or something like that. Or it could be a laboratory hood and so on and so forth. The best hoods are going to be enclosed because more than enclosed they are, the more that of the contaminant will be captured effectively, and the less air you're going to have to move in order to do that effectively. If it isn't enclosed, then you have to use a lot more volume and velocity, capture velocity of air to catch that stuff before it gets out into the room or into the breathing area of the worker. So, but you're going to have all kinds of different ducts. There's a chart in the book, chart 11, which is derived from several books, among them ACGIH's standard for hoods. I'll bring in, one of these days, I'll bring in a copy of it. There should be a copy in the library, as a matter of fact. Maybe I'll track that down. So the hood is going to be the starting point for us. That hood is where the rubber meets the road, where this is all going to work. Okay, so now we have the hood. That hood is going to be a device that's going to make air get pulled into a narrower space. So there's going to be all sorts of turbulence. There's going to be a heat generated, noise generated. There's going to be energy loss associated with that. And that energy loss we call the hood entry loss. So from our perspective, the energy that we're dealing with, up to the point where we talk about motors and fans, energy that we're dealing with are pressures. It's going to be velocity pressure, which is the pressure associated with the movement of the air, and it's going to be static pressure, which is going to be this how much that point in the system is sucking air in. Okay, static pressure is spaciously on this side of the hood, it's suction. On the other side, on this side of the fan, it's suction. On the other side of the fan, it's an outward pressure, static pressure. This is a negative pressure, static pressure. Static pressure is going to get things moving. You don't have sucking, air's not going to move, right? So the more the static pressure is, the faster the air is going to move. There's a trade-off. You're trading off static pressure for velocity pressure. Okay, so static pressure is kind of your potential energy. That's your battery. That's where your energy is coming from. And velocity pressure is the result of that. More static pressure you have, faster the air is going to move, more velocity pressure you're going to have. Okay, so now what we have to figure out is what we have to figure out how much air we need to pull into that hood in order to protect the worker. Okay, and what's that going to be based on? That's going to be based on how far away from the hood the contaminant is being generated, what kind of contaminant it is, and how big this hood is, right? Big hood, more air, and so on and so forth. So we need to know how much suction that we need at the back of that hood in order to generate the capture velocity that we need to pull the contaminant away. So your job, first thing on your list there, your job is to decide what hood to use. Now, I've given you the kind of hood that they're willing to purchase. It happens to be a kind of a square bell-shaped hood. Not a bell, not strictly a bell, but it happens to be square. Calculation is going to be a little bit easier. Okay, and you need to calculate what that static pressure has to be. In order to know that, you have to know the velocity pressure at that point as well, right? Remember, a lot of these things we calculate from the velocity pressure. The static pressure of the hood is equal to the velocity pressure plus the hood entry losses. How do you calculate the hood entry loss? First of all, how do you calculate the velocity pressure? Well, the velocity pressure is going to be determined by how fast the air is moving through this duct. How do we know what that is? Well, we know we have to figure out, based on our chart 11, we have to figure out how much air we have to suck into this duct in order to get the capture that we want. That's Q. Since we know the area of the duct and we know how much air we have to suck in cubic feet per minute, we're going to be able to calculate what the velocity of air is. We know the velocity, we can calculate the velocity pressure. We can either use that nomograph, or we could use a table, or we could use that formula with this 4,005 in the square root, right? So we got a lot of ways to calculate the velocity pressure. Once we know what the velocity pressure is, we can calculate, we know what the velocity pressure is, we can calculate what the hood entry loss is. What's the hood entry loss? It's equal to a K value times the velocity pressure times the density. We're going to forget density. Okay? K value, we're going to get the K value for that hood from the description of the hood in chart 11. Where does that come from? Comes from either the manufacturer, from ACGIH experiments on different kinds of hoods, or it comes from something called the Delaval calculations, which is basically kind of a weird way to just estimate where what area the air is being pulled in from. Okay, but I'm not going to use that very often. I only rarely use it if we just don't have any other data or any other way to do it. So this we can look up, this we can calculate, but we need Q. Okay, so that's the first thing we're going to do. We're going to look up our. I described the contaminant to you. Now you have to say to yourself, what's the capture velocity for this contaminant? If you're grinding and it's big particles, it's going to have to be faster. Air's going to have to move faster to pull those away from the worker. If it's fumes or vapors, chemical vapors or gases, doesn't have to move as fast to capture them because they're sitting in the air there basically. So the capture velocity will be low. There's a chart with capture velocities on it. So we're going to do that. We're going to figure out what our Q has to be, our V, and so on and so forth. Well, now we got a problem. We're at this point now. We know what this suction pressure has to be in order to accomplish what we need to accomplish. Now we want to figure out from here to the fan where we're going to have additional losses that we have to make up. Now, if this were frictionless, no friction at all, if the static pressure that you needed here was -1 inch, then all you would need is -1 inch there because you wouldn't lose any energy, right? So -1 inch static pressure, -1 inch at the fan would translate into static pressure -1 inch here. Problem is that we're losing some of that static, that potential energy, that static pressure. We're losing it as we go along. So the suction here has to be much greater than 1 inch to make up for all the losses in between so that we still left with 1 inch there. So we're going to have to calculate how much this duct we're losing to this duct. We're going to have to calculate how much we're losing to this air cleaner. We're going to have to calculate how much we're losing to this remaining set of duct. Now, very rarely is going to be that simple. There's going to be, you're going to have to go maybe up or sideways. You're going to have to churn. You're going to have to maybe the fan has a different size opening than the ductwork at the back of the hood. You're going to have to either expand or contract the ductwork. So turns, all those things are going to introduce losses. Okay, so how are we going to calculate that? I'm not going to go through these because we're going to do them as we do this. Okay, coefficient entry, we went through all this. Okay, okay, so now what about the ductwork itself? The ductwork itself is going to introduce some losses. How do we know how much the losses are going to be equal to? Well, we're going to calculate that's head loss still. Okay, we got it here, don't worry about it. Okay, now the ductwork itself, the air moving through it is going to introduce some friction losses. In fact, the friction losses are pretty dramatic. Actually, the air moving near the surfaces of the ductwork moves slower than the air in the center of the ductwork. Most of the time when we're talking about velocity and velocity pressure, we're talking about the average velocity across that's moving through that. In the center, maybe moving a bit faster. Okay, and how are we going to calculate that? Well, we also have a chart or a table that gives us how much different kinds of ductwork, usually based on their smoothness and their diameter, how much different kind of ductwork, how much resistance per foot that's going to add, and how much static pressure we're going to lose to that we have to make up. So what are we going to calculate as our static pressure loss that we have to make up? It's going to be equal to the K value for that size ductwork, that material ductwork, and for the roughness of that ductwork. And that's all going to be wrapped up in that K value times the velocity pressure, that's per foot now, times the length. Right? I didn't, in this, the R is separate from the K. The roughness is separate from the K. Okay, usually you'll see it's the same. Like since we're using galvanized, the roughness is defined as 1. So you don't have this built into the K value already. Okay, so that's how we're going to figure that out. We're going to figure out if we got 10 feet of ductwork, how much friction, how much static pressure we're going to lose to that. So now if I go back to my duct, I'll know, well, if the static pressure at the back of the hood has to be -1, if I lose 1 inch of static pressure to a long length of ductwork, now at that point, static pressure has to be -2. So I still have -1 at the start of that ductwork. Any questions? Right? Simple so far, right? Okay. Now there's other kinds of devices that are going to impact this. Transitions, okay? Elbows, turns, contractions, so on and so forth. There's any number of them. Okay. When we make a turn, right? We're going to use a device to make a turn. If you have PVC pipe, usually it's a nice smooth round turn. If you have metal duct, it's usually in sections, because if you can imagine, it's not very easy to, the problem trying to make I just saw a video online of people making globes, like full-size, like office globes in the 60s, 50s and 60s. And they would take projections on paper, and they were like thick in the middle, slivers that pointed on each end, and they might represent like 15 degrees of longitude, right? Longitude, right? So that they were like slivers, like at a point here, widening, and a point at the South Pole. And they would take them, put them onto clay balls that they created, like 2-foot diameter or 3-foot diameter, and they would paste them on. And then they would go meticulously paste them on, make the edges meet, and so on and so forth. And then they would go in and paint the little gaps and stuff like that, so you couldn't see them. Problem is, how do you make something round out of a sphere out of a flat piece of paper that you've printed onto? Same problem here. How do you make a turn with flat sheet metal? You can't. So you do it in sections. And sometimes that ductwork will have either 3 sections, 5 pieces, 4 pieces, 3 pieces, or it'll just be 1 piece where just dead ends against the other, one miter joint just dead end against the other. And notice how the more sections you have, the closer it is to a nice smooth curve. So each one of those is going to have a different level of resistance to flow and loss of energy going through it. So how are we going to calculate what the loss of energy is? Well, the tighter the turn is, right? In other words, if this is a turn that's very gradual, 90 degrees, that's good. A tight turn is going to be worse because it's getting closer to this mitered kind of turn. Okay, so how do we judge that? Well, we put the radius over the diameter. The diameter is the diameter of the duct. The radius is the radius of the turn, right, from here to here, right? So a radius of 1 would be a 10-inch duct with a 10-inch radius. Okay, a 10-inch duct with a radius of 20 inches, smoother curve, would be a radius over diameter of 2. Okay, so that's how you would judge that. You would decide how many pieces you have, right, and what the radius of diameter is, and that's your K value. And now you multiply by your K value by surprise what? The velocity pressure, to get the amount of loss that you have going through that elbow. Right, so it all ties together. Okay, so, and you could have like a number of elbows. Okay, so here's a couple of illustrations of radius versus duct. Okay, sharp curvature, the one on the bottom is 0.75. the radius of the turn is even smaller than the diameter of the ductwork. You see that occasionally. Usually it's a space issue. Okay, you have transitions. You have expansion and you have contractions where you have to change the size of the ductwork. And expansion, you want it to be smooth. You want a tapered expansion. You don't want an abrupt expansion because of a lot of turbulence and more energy loss. And the same thing. Gradual tapers means less losses. Okay, so here's a situation. We actually built one. But yes.
Yeah. Oh,
yes.
Yeah. Why is the calculation so different for contraction and expansion?
Okay, let's think about this for a second. That's a good point. That's a great point. Let me see if I have. Okay, here. Okay, so now let's look at a contraction. When you have a contraction, what's happening is that the velocity pressure, right? The velocity pressure is say it's I'm going to make a number up 2, for instance. Velocity pressure is 2 inches of water here. Now, when you have a contraction, is the air moving through here faster at 2 or slower than at 2? It's moving faster. So the velocity pressure goes up, right? And what happens to the static pressure? You lose static pressure, right? You lose energy. So you have to add static pressure to this to make up for that. Okay. Now what about in an expansion? In an expansion, if I can get one here, I don't see one here, but I'll make one up. In an expansion, the opposite happens. You're going, let's go this way. The velocity pressure slows down, it goes down, right? And since you're slowing down, it goes down, the static pressure goes up. It reclaims some of that energy. When the static pressure goes up, it's actually a negative pressure going less negative, right? Because you're trading off velocity for static pressure energy. That's why in one of them you're subtracting numbers, and the other one you're adding numbers. It's easier to just use the formula than to every time you do it, try and wrap your head around what it should be, right? So just carefully follow the formula, and I'll show you the formula in a sec, the 2 formulas in a second. Carefully follow the formula. It'll avoid you having to think it out every time you do it. But that's what's going on. Very different exchange of energy there. In both cases, you're losing a bit of energy because there's energy lost through that transition. In one of them, you're increasing the velocity pressure and you're reducing the static pressure, meaning making more negative. In the other, it's going the other way around. Okay, but in both cases, you have losses. Okay, the other thing you have is there's transition do's and don'ts, and so on. You also have branches. In this example, we're not going to talk about branches. Branches can get pretty complicated. There's actually a few kind of kludges that we use how to dealing with branches, and one of them is that we want these branches to have, because branches can get very complicated, we want to stick to a certain design criteria. For instance, we want this taper to be a standard 15 degrees, and we want the angle to be from the smaller branch to be joining it at an angle of between 15 and 45 degrees. Okay, no more than 45 degrees. Okay, and we want the smaller branch connected to the middle of the taper. Why do we use those rules? Because when we use those rules, we can use certain formulas to predict their behavior. If we get outside of that, it costs us energy, right? Which means bigger fan, bigger motor, and it also makes it less predictable. Okay, so this is called a standard ASHRAE branch, and we're going to you can all there's certain things you want to avoid, like if you're going to branch into 2 transitions, into a transition, you want to really break it up into 2 transitions, not go opposite each other to cause a lot of turbulence, not have anything more than 45 degrees, and so on and so forth, and not transition and not tie a branch into an ordinary duct. Oh, okay. Okay. Smoothness we talked about a little while ago, and this is kind of similar to the duct we're just talking about, that square, and then maybe not quite square. We're going to be talking later on about blast gates and so on and so forth. So basically, what we want to do is we want to draw our system. Let me play this again. We want to we want to draw our system as we did last week. Okay, and for the time being, let me go back here. I don't want to go past it again. Okay, we want to draw a system. You can draw it like this, or you can draw it as a line diagram. You can just say, oh, little box here, hood, and put a single line, and then the whole thing over here and say, well, that's 10-inch duct. Or an elbow, and you can put a little line saying that that's this, and so on and so forth. Yeah, so what you have there is a few pieces, there's extra graph paper there also. And there's two sets of tables. Each one of these things that are stapled together will give you all the tables that you need. So now, you can either work, you guys, if you have your books with you, you can look up the tables in there. If you don't, you can use these two printed sets of tables. It'll give you the tables you need for this exercise. There's also a full table 11. This one I cheated, only printed the page out in chart 11 that you actually need for this stuff. And what I'm suggesting you do is you can either work as a single group, you can work in two groups, you can work in three groups, or if you're antisocial, you can work by yourself. But I'm going to give you 30 minutes, say about 30 minutes. You think? We'll see. I'm going to give you 30 minutes, and we'll see if that's enough for you to design this duct system up to the fan, from the hood to the fan, with these constraints that we have there. So these are here. If you want to pull these, take these, use them. Okay, share them. Or you can look in your book if you're in your computer. So I'm gonna start the clock.
Yes, here, within this.
Oh, okay, guys, I'm gonna interrupt you because I want to be able to get through this so you guys can get a look at this. Anybody get to the static pressure of the fan yet? Not quite.
Pretty close.
Okay, let's do it. Let's work it out.
Transition, expansion.
You would have been. I'm sorry, I added that in now. Okay, let's take a look at this. First of all, here's my hood. Here's my tapered hood, right? So I have to calculate, number one, what volume of air do I need to move through this hood? That's going to be equal to, I don't have it in front of me, it's going to be equal to, let me get the formula.
3 pi.
Oh, if you're going to use that formula, okay. I would have used the formula at the bottom. I don't really care though. 3 pi times the velocity, capture velocity, right? So the capture velocity is 100. 3 times pi is basically 10.
943.
Is 943? Okay, 943 feet cubed per minute, right? So now where is that going to go? That's going to go through a duct, right? Here's our back of our hood. That's going to go through a duct which is what? 10 inches in diameter, right? So Q is equal to the velocity times the area in that duct. So the velocity in that duct is going to be Q divided by A, which is 943 feet cubed, divided by the cross-sectional area. What's cross-sectional area for a 10-inch duct? Well, we got to change. It's equal to pi r squared, right? You can use the chart, which is 3.14. But R is not 10. R is 5.6. 5.6, right? Okay, guys, want to tell me what it is?
0.8.
0.8. Okay, I'll take 0.8. Seems like a little, 0.8 feet squared. Okay, so you notice feet cubed cancels with feet cubed per minute cancels with feet cubed. You wind up with, what does the number come out to?
Oh, what are you doing?
It comes out to what, about 1,000? 2,000, 0.8 into 943?
We use the second formula and we got a different.
And you had, what number did you get?
formula for Q.
Okay, what'd you get for the second formula?
We got 1527.
1527. Okay, and what was your velocity?
1,500.
Sorry,
1,500.
Is 1,500, oh, you got the overall velocity was 1,500. 1527. You guys using the other formula would have gotten about 1,000. They got 1,500. Well, yeah, but it should have been, right, 943 over 0.8. Maybe you got the area wrong.
Our feet per minute was 825.
Yeah, because we use the other form.
We use the second formula.
Which kind of matches the chart closely.
825 cubic feet per minute? Oh, so you guys were close. You should have gotten around the same number. They got 943, you got 825. Okay, I don't want to spend too much time on this, right?
We don't understand, so you gotta spend time.
Okay. Hold on a second. Let me open up another page here.
Oh, you got the era.
Use pi r square. Convert to the 10 inches into feet, and then use pi r square.
Okay, can we both agree? Can we both agree the two formulas that our Q is roughly 900 feet cubed per minute? Right? That's kind of in between your two readings, okay? Everybody's okay with that? Okay. So they got 847, you got 9 something. Yeah. Okay. Well, how much did you guys get?
825.
And they got 9. Okay, so it's really, yeah. Yeah, it's kind of in between. It's kind of in between. So I'll call it 900. So now the velocity is equal to the volume over the cross-sectional area of the ductwork. Right? That's just another way of writing Q is equal to the velocity times the area. Right? Okay, so the velocity is equal to 900 feet cubed per minute divided by the cross-sectional area of a 10-inch duct. 10-inch duct, what's the cross-sectional area? There's a couple of ways I could do that. Simplest way is go to chart 5. Right? Chart 5? And chart 5, 5-inch duct, the cross-sectional area of 5-inch duct is, I got the wrong one. Where is it? Point. Oh, I'm sorry. Diameter. 0.5454. I'll call it 0.55. Is that right?
No, look, if you go through 900 instead of 1,000.
Divided by 0.55. Okay. Hey guys, can I get your attention? The cross-sectional area of a 10-inch duct is 0.55 square feet. Everybody agree with that? Is that right?
Sure.
Okay. So 900 divided by 0.55 is going to about double that, right? So the velocity is equal to, work it out, 900 divided by 0.55.
1800.
Okay. 1800. No, it's not 1800. A little less than 1800. Okay, let's call it 1600.
Yeah, 16.
Okay, 1600. Okay, what's the velocity pressure? Okay, we could either use the formula or we could go back to chart 5. So if the velocity is 1600, then the velocity pressure is roughly 0.15 inches. Okay, good enough? 0.15. 0.15 inches of water. 0.15. Okay, so the velocity pressure at this point is 0.15. Now, what's the static pressure at this point? The static pressure, right, is going to be equal to static pressure, positive value of static pressure is going to be equal to the velocity pressure plus the head loss, plus the hood entry losses. What's the hood entry loss equal to? Hood entry loss is equal to, let's say it's going to be 0.15 plus the hood entry loss is going to be equal to K for the hood times the velocity pressure, which is 0.15. What's K for this hood?
0.25.
Do I need to go there and look?
And then 90 degree, and it's here, so it's 0.25.
Okay, how much is it? 0.25? Okay, there it is right there. 90 degree, that's the angle of that slope. 0.25 is K. So our static head pressure that we need to accomplish is going to be, 0.25 times 0.15, a quarter of this, which is 7.5, which is about 0.375. Okay, 0.15 plus 0.375, 0.0375, which comes out roughly to our static head pressure, 0.15 plus, good entry loss, 0.375, let me see, 0.15
Times 0.25.
0.15 plus our hood entry loss, which is equal to K times our velocity pressure, which is 0.035, So our static head pressure has to be 0.185 inches of water. Everybody okay with that? Right? This has to be negative 0.185 inches. And the velocity pressure is equal to plus 0.15. Are we okay at that stage? Okay, what happens next? What happens next is,
Professor, it's not 0.0375, it's 0.375.
but wasn't that a entry loss? I had to add it to the velocity pressure. Where am I?
Entry loss is 0.375.
What entry
Then
loss is?
you gotta add it to the VP, which is what, 0.25?
Uh, what was my formula for hood entry loss again?
0.25.
Yeah, my hood entry loss was my velocity pressure plus K times.
V K times VP times.
I'm having a senior moment here.
No. K times VP times.
My hood entry loss, HE, is equal to, what's the formula?
K times VP.
Right, so VP is 0.15 and K is 0.25.
Yes.
So that comes out to 0.375.
Yeah.
Okay? Now, in order to find the velocity, in order to find the static pressure I need here, my static pressure for the hood is VP plus our 0.0375. So it's 0.15 plus 0.0375 for a total of 0.185.
Oh,
Okay? Everybody on the same page there? Okay. So now we go 100 feet with 10-inch duct. So now I have to figure out what my loss is going to be due to that 100 feet of duct. Okay, so let's go to chart 5 again. Where is chart 5?
The first one's only 10.
the first one's only 10 feet.
Oh, the first one's only 10?
Yeah.
Okay, 10 feet. Okay, so for 10-inch duct at 0.15 velocity pressure, my K is equal to 0.024. So the loss from 10 feet of duct is going to be 10 times 0.024, which is 0.24. Okay? So that means,
Question right off the bat.
yes,
Can we calculate the duct loss for the addition of all the 10-inch duct?
yes, you could. If you wanted to just add up the number of feet and do it all at once, you could. Okay? Okay, so now my end of that 10 feet, now my new static pressure is going to be 0.24 bigger than that, which is going to be 0.24 bigger than that. 0.24 is going to be 342.425. 0.425 inches. I got the 10 feet of ductwork. The K factor was 0.024, right? I multiply that by 10 feet and by 1 for the roughness, right? And it's 2.24.
And you have to multiply VP too. You have to
Oh,
multiply.
I'm sorry. I didn't multiply by VP, did I?
Right.
Which is 0.15. Oh, you're right. 0.15. Yeah. Somebody want to give me what that is?
0.036.
0.0. So it comes out to point, what?
Yeah,
0.036. 0.036. So it's 0.185 and 1 point plus 0.036, which is, what is it then?
Point
0.03 is going to be 0.2.
2.1.
0.21. Okay, I'll call it 0.21. Close enough. Negative 0.21. What's the velocity pressure? Has it changed? The velocity pressure is still 0.15 because it's still moving the same speed the air. Okay? So next, what happens next? After that, 10 feet to a 90-degree turn, 3-piece galvanized iron elbow. So there's a turn. I'm going to show it any direction I want. There's a turn here, and right after the turn, what do I have to calculate? What's that going to do to my static head pressure that I have to maintain? Okay, well, what is it going to do? It's K for the elbow times the velocity pressure is the amount of static pressure that I have to add or that I'm going to lose. So what is K for that elbow? 3-piece elbow, 3-piece galvanized 90-degree elbow. 0.34
Yeah,
times the velocity pressure, which is 0.15. right? So that's roughly about 0.05. So I have to add 0.05. So now my static pressure is up to 0.26, negative 0.26. So what happens after that? From there, we go, turns up at a radius. Oh, I'm sorry, I forgot to tell you, it was R. What was R? R was 15 over 10, so it was 1.5. Okay, good. Into another duct, 10-inch duct that travels 20 feet straight up. Doesn't matter. At sea level, it doesn't matter. So the density is going to be the same, 20 feet, no problem with going up or sideways. So it's going to go straight up. Now, fluids might be different, right? Fluids heavy, dense, right? So if you're pumping crude oil, the fact that a pipe's going up instead of horizontal is going to make a difference. For us, for air, it doesn't make a difference. Okay, so it's going to go 10 feet up for 20 feet up, 10-inch duct. So we're just going to repeat what we did before. K for the pipe was what again? 0.024, right? Times the number of feet, which is this time 20. So our loss is going to, roughness and so on and so forth, times the velocity pressure, 0.15. So what does that come out to? 0.15 times 0.024 times 20. Do I have to do that? I was hoping you people would have done this. It's what, 0.072? 0.072. I'm going to call it 0.07. So now we have to add, for that extra 20 feet, we have to add another 0.07 to our static pressure. So now we're up to negative 0.34, right? So what happens now? We go to another L, right? Another elbow. So what's going to happen at that other elbow? Okay, coming out of that other elbow, what are we going to do? Well, again, it's K for the elbow times the velocity pressure is what we're going to lose. Except this time, the elbow is 5-piece with a radius to diameter of 1, right? So what's the K factor there? K factor for that? Let's equal to 0.33?
Yes, 0.33.
Times 0.1 times 0.115, our velocity pressure. That's equal to, again, 0.05 roughly. Not much of a change, right? Okay, so 0.05 added on to this. Now, at that point, coming out of that elbow, where our static pressure now has to be 0.39 inches in order to maintain the 0.185 that we needed at our hood. Okay, we're not done yet, right? What happens next? We connect now. Okay, we go now we travel 100 feet. Now it goes 100 feet, right? So what is it again? Now it's going to be K for galvanized iron, which was 0.024, right? Times our velocity pressure, times 100 feet. Okay, which is going to be, our velocity pressure is 0.15. So a quarter of 0.15 was 0.0375 times 100 is going to be, oh wow, look, 3.75 inches. Wow, big loss there, right? Because of that big run of duct. So now it's 0.39 plus 3.75. At this point, what are we at? Am I right about that? 0.24 times 0.15 is 0.0375, correct? Times 100. Oh no, it's 0.024. I'm wrong. It's 0.0375. Right? It's 0.024 times 0.15 times 100. So it's 0.0375. So 100 times that is going to be 0.375. Am I right? Okay. Help me out with this. Okay. So let's assume we're right. Okay. So 0.34 plus 0.375. I'll call that 0.3. 0.77, okay, negative 0.77 inches. Now we go into a filter. What did I tell you the pressure drop was across the filter? Okay, so now at this point outside of the filter, we're at negative 1.77 inches. That's realistic. Filters have big, air cleaners and filters could have, depending on what kind they could have a pretty big pressure drop. Okay, so now what do we do when we come out of there?
We did this one already.
With the feet of 10 inch.
20 feet of 10-inch duct. Didn't we just do that? Yeah. And what did it come out to be? What was our loss there? Anybody remember?
0.0.
0. Point,
0.072.
0.072, 0.07. So now at the end of that, we're up to 1.84, I'll call it. Negative 1.84 inches. And what happens now? From that point, 10 inches, by static pressure loss. Filter discharges a 10-inch duct, travels another 20 feet to a 30-degree reduction from 10-inch to 8-inch. Okay, so now we have our reduction. Okay, now this is our complicated part, right? This is 10-inch, this is 8-inch. Okay, so the velocity pressure at 10 inches is still 0.15. What's our velocity pressure at 8 inches?
0.2.
Well, let's think about this. What's going to happen? The same amount of air has got to go through less space, right? So what's going to happen is our Q, remember what our Q was? That hasn't changed. 1587, right? Now we're going to divide that by a different area, the area for 8-inch duct, right? So and that'll give us our velocity, which will tell us what our velocity pressure is. So let's figure out what that is. What's the? I'm going to go to chart 5.
We said Q was going to be 900.
Yeah.
So you see between the two. Yeah, he's writing down.
I got the wrong. I have some. You threw so many numbers at me before. I lost track. 900. You're right. So now instead of 8-inch duct, we got 10-inch duct. We have 8-inch duct, and we have a velocity pressure of 0.15. Right? Excuse me. We have a Q. What's our volume? Volume flow rate of, what was the volume flow rate again? 900. So now with 8-inch duct, we're talking about a velocity pressure of, it looks like about 0.3. I'm going to call it 0.4. Sounds good. Okay. Oops. 0.4. Velocity pressure now is 0.4. Okay. So what's our change in velocity pressure? Is 0.4 minus 0.15 is 0.25 inches. Okay, so what is our formula for our loss there? Our static pressure 2 is equal to static pressure 1 minus the difference in velocity pressure, 0.25, minus 0.25 times the K factor based on the contraction. So now let's look up what the K factor is for that contraction.
0.13.
I don't, do I have it here?
30 degrees, right?
Yeah, 30 degrees.
Chart
Chart 17, I have it here somewhere, I think.
You got it. For
Chart 17. Did I give you guys chart? Oh, there it is. This chart 17. Yeah, chart 17. It's a contraction. I said it was 30 degrees, 0.13. So it's 0.13 times the difference in the velocity pressure, right? 0.13 times the change in velocity pressure. So a third of that 25, say about 0.08. So static pressure 1 was negative 1.84 minus 0.25 minus 0.08. Now, if it's expansion, it gets more complicated because one of those numbers, this number turns positive over here for velocity pressure. So you have some regain. Okay, so what does this come out to?
I think I know. So it's supposed to be.
It's the static pressure 1, which is minus 1.84. That's what we're up to. Minus the change in velocity pressure, the difference between the before and after velocity pressure, which is 0.25, minus the K for a 30-degree contraction times the velocity pressure, change in velocity pressure, times the change in velocity pressure is 0.25. That's where I got that 0.08.
Sorry, can you repeat that for me?
I'll do that again.
This is a different formula from what they have.
Okay.
He understands. So
Static pressure 2 is am I misleading you here? Static pressure 1, right? Minus the change in velocity pressure minus K times the change in velocity pressure.
Oh.
That's the loss.
Okay.
right?
Now
So
it's
static pressure net one was minus 1.84. That's where we started going into the contraction based on all our calculations. Minus the change in the velocity pressure, which was zero point 0.4 minus 0.15, which is minus 0.24, 25 rather, minus K, which was 0.33 times the velocity pressure, which was 0.25. So it's roughly 0.08, I'm calling it. Okay, 1/3 of the 0.25. Okay, so what does that add up to? Static pressure 2 now is what?
Oh, I think it's 0.13 is okay, right?
I'm sorry?
You just put it 30.
But you have to multiply it by the change in velocity pressure.
Right, but it can't be that 0.08.
Did I make a mistake on the K? Is that what you're saying?
No.
K for 30 degrees is 0.1. Who said, did I say 0.33?
No, you said
Oh, did I use the wrong number? Okay, hang on a second. Let me go back. K is 0.33. It's 0.13 times the velocity, change of velocity, 0.25.
Yeah.
So it's about a tenth of that. So point, 0.03?
Oh.
Okay, 0.03 is good. Okay, so let's add all that up. What do we wind up with? Is static pressure 2 coming through that contraction. What does that equal to now? 2 point, what was that? 2.15? Yeah, that's close enough. 2.15. Negative 2.15. Now we got a short run of ductwork to the fan, but what was it, 10 feet?
Yeah.
And we already did that. How much did that contribute at 10 feet? When we were over here, it went from point, what's that?
It was a different diameter.
Oh, it was different diameter. You're right. Different diameter, different velocity pressure, right? So let's look up our K value on chart 5, right? So now we're dealing with ductwork that is 8 inches in diameter, and our velocity pressure is 0.45. So our K factor is 0.03. 0.03 times 10 feet is 0.3, right? Okay, so that's 0.3 that we've lost that we have to add back in for that loss through that last 10 feet of ductwork. It's more because it's a smaller diameter duct and it's moving faster. 0.3. So at our fan, we need to have a static pressure of negative 2.40. 5 rather. 0.3. Right? You get that right? I forgot what that number was already. Just flipping that page. I'm calling it about negative 2.5 inches. So now I need a fan capable of moving 900 cubic feet per minute of air with a suction pressure of negative 2.5 inches at the fan. That will give me, after I go through all of these various losses, that'll give me the capture velocity I need 12 inches from that hood. That's what we're trying to design here. Now, let me ask you something. What was the velocity going through here again? It was something like how many feet per minute? It was 1,500 feet per minute. What would be a problem if this was a grinder instead of like fumes from soldering? Why would 1,500 feet per minute be a problem? We need more, not for the capture, but possibly because we need transport velocity so that particles don't settle out in the ductwork. So we might need to have 2,000 or 3,000 feet per minute of velocity. How would we take this and make it that big? There's a couple of ways we could do it. We got to pull more air, right, which would kind of affect the hood performance. Or we can make the ductwork smaller so that the air is moving faster through the ductwork and we achieve our velocity. So now what does that tell you? That tells you the first time you design this, you may have an issue and it may not work right. You may not have the transport velocity you need. What does that mean? That means you have to now resize the ductwork and go back and do it again. Now, are you going to do that every time and have to worry about that? And it's going to be a real pain in the butt. You're going to spend a lot of time doing this, right? Okay, is that what's going to happen here? Well, can you see this? Am I on screen now? I guess I am. Yeah. So now, what I'm going to say now is that, okay, we have that situation now. Now, is that what I'm going to do every time? Well, what we're going to do every time, I'm going to just want to start this PowerPoint and then you guys can escape. I'm sorry we went so late. I'm sorry I gave you so much time to put. I'm sorry I put in that last transition. Is what I'm really sorry I did. Let me find my PowerPoint here.
We need to have these notes typed because we can't read this.
That's true.
I understand what you're saying. No, actually, I got something better for you. You're going to submit this as assignment 2.
Oh, okay.
You're going to redo this yourselves. Make a drawing up, submit it as assignment 2, and show all the calculations and details. I just want to show you one quick other thing here, and that is that after we get through this whole thing, shoot, after we get through this whole thing, we are actually going to be. We're going to be doing many of these calculations using a spreadsheet. And the spreadsheet will have all this worked out. So if you put in that it's 8-inch duct, it will have the table for the K values built in. So you won't have to look it up. If you put in that the Q value is this and the duct size is this, it will calculate the velocity, pressure, and the velocity for you. So you won't be doing this by hand. The spreadsheet will be doing the heavy lifting for you. Now, if you want to be adventurous and you want to go to the spreadsheet, see if you can't get it to work, you're welcome to do it. You can sit. There is a spreadsheet for this. Okay. I just wanted to point out one other thing to you, that there's also. Now I'll talk about this next week. We did enough today, I think. Okay. I just wanted to point out that there's also situations where you are going to have very frequently many hoods on the same system, on the same fan. Like this. It's not there. Great. Is it back?
Wow.
Right. You're gonna have many hoods on. You're gonna have many hoods on the same fan, and they will be joined by connections, branches. So you're gonna want to design a fan to balance all of these, so you don't need any adjustments or dampers in there. So you get the right amount of airflow from each one of these different kind of hoods. That's going to get very complicated to do. That's why the spreadsheet's going to make things so much simpler. Okay, so you guys think you're going to be able to do this at home when you have a little time to sit down and really calculate it a little bit more carefully? Yes? Yes? I can do stuff by Skype or something like that, or go to meeting. Yeah. Okay, I'll tell you what. I'll tell you what. I'll make it due. So don't freak out, but I'll make it due on Sunday night, this assignment. On Monday night, I'll do an online thing where I go over it again. Well, I'm also going to post this online, but I'll go over it more. I'll have the chance to go over it more carefully and actually do all the calculations myself.
On Sunday night.
I'll make the assignment due on Sunday night. But Monday night, I'll do an online session that I'll record. Okay, so you can see the answers. Yeah, I'll do it live. You can tune in live, or you can watch it later on.
So we're gonna do the session after we submit it?
That doesn't make sense.
I'll make it through Tuesday night. I'll make it through Tuesday night, and I'll go over it on Monday. Okay. You guys have no sense of adventure. I'm sorry.
Is the meter gonna be similar to
Is what?
the meter?
The midterm? The midterm will involve some design issues and questions. It'll have a little bit more stuff about density and, it'll have a few questions and stuff like that. I'll try and come up with some sample questions for the midterm.
Are we gonna take it home or are we gonna do it here?
I haven't decided that yet. Since this bit basically is a design course, I think that there's at least gonna be a good portion of it that's take home. Right? Maybe I'll have a little bit of it in class, but a lot of it'll be.
That's
Yeah, because how you gonna sit here and do,
we're
yeah,
gonna
it's good.
have to do it.
Yep, I agree. Okay. Now, are you guys getting closer to the point where if somebody called you up in a couple of weeks and said, "Oh my God, I need a hood designed right away," that you could go over and design a hood for a person?
It's the transitions. The transitions are confusing.
Yeah.
Those glasses that have to be combined.
Yeah. Yep. And the spreadsheet's going to help you on that. Make it less chance that you're going to make an error, like the silly errors I was making with, like adding and subtracting and forgetting to multiply by VP or something like that. That'll take a lot of that kind of error away. those spreadsheets. But you need to understand where these formulas come from. Otherwise, the spreadsheets won't do you too much good.